situation again. So suppose, so more about argument function. Variation of argument. So suppose we're in this situation that we have gamma 0, 1 to say C0 that parameterized path, and we chose an argument function. Which is the same as chose a lifting of the path. Of gamma tilde 0, 1 to C with exponential of gamma tilde. Well, if you want. This being gamma. So we know that such section is the same as a choice of argument. Now, suppose we have two such. So gamma tilde 1 and gamma tilde 2 are two such lifts. So we know that every lift is uniquely determined by gamma tilde of 0, by the lift of the 0 point. So if gamma of 0 is at 0, then given a choice of y0 x of y0 is x0, we get gamma tilde uniquely. So it means that choices of lifts are in bijection with points in the fiber in of x0. So if we choose one point, then the path starts in a unique possible way. But there are, since we're talking about not random covering but exponential map, so such points differ by 2 pi I(n). Right? So if x of gamma tilde 1 of 0 equals x of gamma tilde 2 of 0, it means that gamma tilde 1 of 0 minus gamma tilde 2 of 0 is 2 pi I(n) for some n. N in Z. But it follows that for any other t, difference will stay the same. So it should be, it should be 2 pi I k for some k, but k equals to n. So the difference in the starting point stays the same everywhere. Why? Let me prove this. Indeed. So this difference, gamma 1 tilde minus gamma 2 tilde, is a function from 0, 1. So at every point this function takes values in the set 2 pi I natural number, integer number. 2 as a set 2 pi I n, and in this. So it's a continuous function. And the set is discrete. So, evaluate. So with values in a discrete set. So if you think about it, this is possible in only one situation. Namely, since the interval is connected, this function is bound to be constant. So, in other words, if gamma 1 tilde of 0 minus gamma 2 tilde of 0 is 2 pi I n, then for any t, gamma 1 tilde of t minus gamma 2 tilde of t is 2 pi I same n. And it follows from the fact that the interval is connected. Now, in terms of argument function, so corollary for the argument function. For argument function gamma. So if you remember, our gamma was basically imaginary part of this gamma. So then, for some gamma tilde, for some lift, now arg gamma prime minus arg gamma double prime then is imaginary part of gamma tilde say prime minus imaginary part of gamma tilde double prime. These are two different lifts of gamma. So gamma tilde prime, gamma tilde double prime, two different lifts of gamma. So let's see by our previous considerations. So this is imaginary part of 2 pi I n. So it's 2 pi n for some n. So two argument functions differ by a constant, which is 2 pi some integer number. Proved. double prime two argument functions. Along gamma. And then there exists a unique n in Z. The difference is constant. We can write here Z. So this leads to a definition. So given a parameterized path, gamma, say AB or 0, 1, let's say AB, 2, sigma 0, variation of argument along gamma is simply so we need to take the difference argument gamma of B minus argument gamma of A. So we take difference of arguments at endpoints for this parameterized path. Now the remark is that the definition is correct. Namely, it does not depend on a choice of argument function. So if we have two of them, so let's say that one of them is, so one of them differs from the other by 2 pi n. Oh, sorry, there's no I here because it's already magnified. So 2 pi n. Then r double prime of B minus r double prime of A is r prime of B minus r prime of A plus 2 pi n minus 2 pi n. So these cancel out, and the difference is the same. So variation of argument stays the same, even though argument functions could be different. Very good. So special case of this is winding number. Let's talk about special case. Winding number around 0. So definition. So if gamma is a path, 0, 1 or AB, and suppose it's actually a loop. So gamma of A equals gamma of B. And then winding number around 0. 0 is this point around which we wind. Gamma is just variation of argument along gamma. Yeah, that's it. So the geometric picture is like this. We have this complex plane, and we have thrown away 0. Then there are loops, so they go like this, or like this, or so direction is important somehow, or maybe like this. The only thing is that they are loops. Then it will turn out that, first of all, for this number to be non-trivial, the point 0 should be inside this loop. And second, intuitive picture is this winding number, defined like this, is exactly how many times you go around this, the point 0 along the loop. So it certainly depends on parameterized loop, but it will turn out later that parameterizations only change, reparameterizations only change the sign depending on direction of winding. If you change the sign to opposite, then winding number will get negative. So, maybe I should divide also. So it should be an integer number, so let's divide by 1 over 2 pi. So this is the winding number. And since variation of argument is defined uniquely, the winding number is also defined uniquely. So, remark, a bit later we will get an analytic expression for this winding number. And you can guess what this expression will be, because we already had it at one of the exercises. We did integrate along such loops around 0 the function 1 over z, and we saw that these integrals depend on how many times we go around 0. These loops were special, they were along the circle, but we know by now that such answers are supposed to be flexible, so you can draw this to any closed loop. Good. So we talked about argument. Let's talk about logarithm. It's a very closely related issue. Let's talk about logarithm of complex number. So logarithm. So again, our picture is that we have exponential function going from c to c without 0. And we have some open subset here, U, maybe a domain. And then the definition is very easy. So far we talked about picture where there was no holomorphic functions involved. So we talked only about continuous functions. So it was topology. Now complex analysis returns. So definition for u in c without 0, log u is a holomorphic section of x. So in other words, it's a holomorphic function such that f of log u of z equals to z, for z in u. So let me remark that the difference from section is that so earlier our sections S of x were just continuous. Another remark is that for general domain, u logarithm u may or may not exist. So, as we see, there are many logarithms. So, in particular, they depend on a choice of domain, and even there, they are non-unique. So let's fix domain. So this is called principal logarithm. So our choice of domain is this one. So we called it earlier C sub phi. So we threw away the ray in the horizontal direction starting from 0. But we could have done something completely different. We could have thrown away different ray. We could have thrown away basically any path going from 0 to infinity. But let's do it like this. So now I'll define my choice of logarithm by so it will be a function. So how to define this principal logarithm? So first of all, choose principal argument. Now, in such a way that the values of arguments is from minus pi to pi. So then the claim is, so we chose this function. If we put log of z equal to well, real logarithm of absolute value of z plus I this argument, then this is a logarithm function, is a logarithm function. Cp, i.e. it is holomorphic. So first of all, why is it a section? So things to check. Let's prove. So first of all, it should be inverse to, it should be a section. So x will be x of the sum now exponential function is multiplicative, so this is times now real logarithm function is inverse to exponential function. So this is just absolute values of z. And by definition, this is the well, this is the argument of z. And this is the presentation, so this is polar presentation of z. Yeah, so then this is it. This is one thing. Now the second thing is why it is holomorphic. So I need to explain that it's holomorphic. So, to explain that log belongs to holomorphic functions on Cp and find its derivative, just recall. So choose a subset in C. So we know this subset, it's a stripe. So from -5 to 5. So on which exponential function is bijective. So then we already had the theorem about inverse function in holomorphic world. So by chain rule and the inverse function derivative formula. This log, which I talked about, is inverse to exponential function as functions between. So I need to give a name to this stripe. Let me call it G. backwards. So then log is also holomorphic. And then to see its derivative, you write log x of u should be u, and then you differentiate. So since it is differentiable, then you differentiate and you get log prime x of u times x prime of u, which is x u, equals 1, which gives us that log prime x of u is 1 over x u. But so u was a coordinate here, and x u was our coordinate z here. So we just substitute, and we get that log prime of z is 1 over z. So the logarithm we were talking about, which we defined just from first principles, is indeed satisfies the property that it's not only holomorphic, but its derivative is 1 over z. This actually leads us to discussion of logarithms in other domains. So, other logarithms. This is a theorem where G in C without 0 be a simply connected domain. Then there exists LG, G to C, a logarithm. So a holomorphic section of C x C star defined on G. Moreover, LG prime is 1 over z, and the proof is so by so we have G is a subset. G is a subset in C without 0. So then 1 over z is a holomorphic function on G. Then and G is simply connected. So there exists a function, a holomorphic function, which is primitive for 1 over z. So with LG prime equals 1 over z. Now choose it. So choose this primitive. Now let's prove that it's a logarithm. It's just a calculation. So let's do it. So let's take a function phi of z, which is z x of minus Lg of z. Now let's differentiate it. So phi prime is x minus Lg of z plus x z x minus Lg of z. Then times Lg of z prime, or minus Lg of z prime. So then this becomes x minus Lg of z minus z times 1 over z x minus Lg of z, which is 0. So we have a constant function. So phi is constant. You can evaluate it and see that in fact 1, which gives us z times 1 over x Lg of z equals 1. So that's what we really needed. It's a proof of existence of logarithm. Yeah. So then this standard, so we are coming back to complex world. We were doing more geometry and topology than complex analysis today, but we're returning to the complex world. And the last thing to say is that let's take principal logarithm of 1 plus z in the domain like this, has Taylor expansion, which is the one you know. Z minus z squared over 2, so on, plus minus 1 to the n, z to the n over n, plus so on. The standard expression for logarithms. And I think it's the last thing to talk about today. So proof, you just start differentiating to 0. So start taking derivatives. Prime is 1 over 1 plus z, and then you can differentiate this function, and you know its derivatives, and then we know that any function is expressible, so take values at 0. And then we know any function can be expressed as Taylor series in the radius of convergence. The radius of convergence. But these series converge absolutely inside this domain. So somehow we started from a rather exotic definition of logarithm as section of the exponential map, but then we came back to what we're supposed to know about logarithm as something given by some of these series, or something which is whose derivative is 1 over z, and so on. Good. So I am a bit behind the schedule. I lack the discussion of powers function, and I'll do it on Tuesday. Yeah, and so I should put it like this.